In this tutorial, we will show how to perform a power spectral density analysis with SAP 2000. The model is a 50-foot tall pole with a random forcing function applied at the 30-foot elevation. The forcing function is a power spectral density curve with a magnitude of 300 pounds squared per hertz over the frequency range 0 to 5 hertz. The goal of the analysis is to be able to plot the spectral density curves of the results, as the square root of the area under these curves will give us the RMS values that are needed for checking and design. We start by making sure that we are working in pound-inch units. Next, select the File, New Model command, and click on the Grid Only option. We will lay out a grid with one space in each of the X and Y directions and 5 spaces in the Z. The spacing in the Z direction will be 10 feet or 120 inches. Next, we define the material property of the pole, which is made of steel. We will add a new material called pole. The mass will be calculated from the weight of 0.28 pounds per cubic inch. The modulus of elasticity is 30 million psi. Now we will define the properties of the pole section. We start by adding a general section. Our section will have an area of 10 square inches, a moment of inertia of 200 inches to the fourth, and shear areas of 10 inches squared as well. We can skip the other variables as they are not pertinent to our model. Name the section pole and make sure that the material is set to pole as well. You can ignore the depth and width dimensions as they are for display purposes only. Next, we can draw the pole. We will draw it as 5 segments, each 10 feet long. The base is fixed, so select the bottom joint and assign a fixed restraint. A check of the analysis cases shows that the program currently has 2 defined. We may delete the dead case as we will be doing a dynamic analysis only. Select the modal case and click on the Modify Show button. Change the maximum number of modes to 3 and click OK. For this example, we will do only a planar analysis in the XZ plane. We are now ready to run the modal analysis. It is important to note that we are running a modal analysis only at this time. We are not doing a power spectral density analysis, as we require frequency information from our model prior to plotting spectral density curves. With the analysis complete, we need to determine what frequencies fall under our 5 Hz cutoff on the random forcing function. Our log shows us that just 1 out of the 3 modes at 1.389 Hz occurs below the 5 Hz cutoff. Next, unlock the model so that we may define the items needed to do a power spectral density analysis. Start by replacing the dead load case with a Psd case. Select the joint at the 30-foot elevation and assign a unit load in the X direction. Now go to the Define, Functions, Power Spectral Density command and click on the Modify Show button for the default uniform Psd function. For our analysis, the value will be 300 from 0 to 5 Hz, so modify the existing function. Note the coordinates are displayed in the lower right-hand corner. The last item to define is a Psd analysis case. We will add a new case called Psd. Make sure that the analysis case type is set to power spectral density. Under the loads applied, note that we will be applying the previously defined uniform Psd curve to the Psd load case, which is the unit load in the X direction. The scale factor is 1. One of the most critical steps in the data definition process is setting the frequencies. This controls the shape of the output spectral density curves, and thus ultimately the RMS values. We will start with a basic selection, but we'll need to add significantly more points, especially around the frequency of the model. We will use the Add Specified Frequencies command. We are adding in frequencies between the whole number values of 1 through 5. It is important to add in smaller increments around the fundamental frequency of the model. Once all the frequencies are added in, note the heavy concentration around the fundamental frequency of 1.389 Hz. The last item to input on this form is the damping, which we will set to 0.04. We are now ready to run the analysis for the power spectral density input. Once the analysis is complete, select the joint where the forcing function was located and go to Display, Show Plot Functions. Here we will plot the spectral density curve for displacement in the X direction. Note that the program knows to plot the values against frequency due to it being a Psd analysis. Note how narrow the curve is and why it was important to include numerous points around the fundamental frequency. What we are ultimately interested in is the square root of the area under the curve, which gives us the RMS value of the displacement. We can get this value by selecting the joint once again and asking the program to display the deformed shape. A right-click on the joint shows the RMS displacement value is 0.32 inches. A right-click on the top joint gives an RMS displacement of 0.7 inches. We can obtain the RMS values for the forces in the model by going to Display, Show Forces command and selecting the Psd load case. In this case, the maximum RMS moment at the base is approximately 40,000 pound-inches. This concludes this tutorial.